start and then we'll go. Okay, so up until this point, all of our permutations have been used to count the number of distinguishable arrangements. So again, if I have the order of things and maybe I have all the same elements in there, but if they are in a different order, it counts as a different arrangement. And a permutation happens when we choose R of n distinct items. So I choose a select few of my total items. Now, sometimes it happens when my items are not distinct. So what happens if some of my items are identical? So what I mean by this is up until this point, we've always been organizing things like different people into different roles. Maybe they're all sitting somewhere. We did some work with playing cards where all of the cards were different. But what if not all of the items are different? What if we have some that are exactly the same, so it doesn't matter where they get put in the order? So it kind of doubles up on some of our orders a little bit. So let's start with an example. So we're going to start by listing all the permutations of the word, for lack of a better term, LOL. To start, we're going to use a subscript to differentiate between the two L's. So we're going to start there so that I can tell which one is using the first L and which one's using the second L. And then we'll try to get a sense of how many options we have. So I'm going to write them all out. So I have L1, L2, O, L1, O, L2, O, L1, L2, like that. Then I could also have L2, L1, O, L2, O, L1, L2, oops, O, L2, L1. So when I distinguish between the two L's, I have 6 possible options here. Now, this doesn't always happen, right? Usually if I'm rearranging letters in a word, I wouldn't distinguish between the two L's. So let's see what happens when we cannot use a subscript to identify the two different L's. So the first one would just be LLO, LOL, and OLL. You'll notice that this significantly reduced the number of possibilities that we have. So it's very, very important that we know if we're distinguishing between them or if they're going to just be identical elements. So it's very important that we know that ahead of time. Now, this kind of situation happens all the time, especially when we're rearranging words, just because we do have lots of identical elements in that we could have things that have the same letter. So for example, we're going to look at these 4 words, and I'm going to show you how to address the identical elements, and then we'll look at the formula. So our first one here, mace, there are 4 different letters. So when I rearrange them, I can just rearrange them and use 4 factorial to get my final answer. Just like that. So in this case, there would only be 24 ways to rearrange the word mace. Now for our next one, we have mass. So in this case, I have 4 letters still. So I put that 4 there, but I have that S that occurs twice. So to address that, I need to divide by 2 factorial. The reason I'm dividing by 2 factorial is that the S, it doesn't matter which one it is. So what happens is I can swap the S's, and then dividing the 2's accounts for that and not double counting where the s's are swapped. So it just addresses for all the ways the s's can move around, and we want to divide those out and not account for them. Similarly, for the word SAS, I have 4 letters, so we have 4 factorial, but I have 3 s's, so I want to divide out all the way those 3 s's could be arranged, which would be 3 factorial, right? Because I don't need to account for all the ways that the s's could be arranged because they're all the exact same. So there is a formula for this, and that's what we're going to talk about now. So this is what our formula looks like. So we have n factorial all over a factorial, b factorial, c factorial, and that just continues on. And this happens where n is my total number of elements in the set. And then ABC, and that could continue with however many identical items I have, is the number of identical elements of each type. So I find these easiest to do with an example. So when we go through the example, we're going to do it in 2 very similar ways. We're going to do it using the formula, but I also want to do it using the box technique too, just so you can see 2 ways to approach it and then choose whichever one is best for you. So for 1, we want to determine how many 7-digit numbers can be made from the digits 6, 5, 4, 3, 2, 5, 5. And all of the digits must be used. So let's start by using the formula to determine this. So n is my total number of elements. So there are 7 total elements. And now we need to address our identical elements. So A is going to be my number of identical elements. And I have 1, 2, 3 5s. So I'm going to have number of 5s, and that is equal to 3 5s. So now we can put this into our equation. So we have n factorial all over a factorial. In this case, it's only a because that's the only identical element we have. So we have 7 factorial all over 3 factorial. And if you put that into your calculator, you will get 840. There we go. Just like that. Now, the other option that you can do is you can still use the box technique, and I'll show you the other option if this helps you. So we are looking to make a 7-digit number, like that. Now we're going to count the number of ways to start, just as if we didn't have any identical elements and we weren't worried about that. So we would have 7 choices for the first number, and 6, and 5, 4, 3, and 2, and then 1. And because I need the first number and the second and the third and the fourth, I multiply them all together. So that gives me 7 factorial. But now I need to account for the fact that wherever the 5 goes, it would be the same. So if I move my 5s around, nothing changes. So I need to divide out the information for my 5s. So I have 3 5s, so I divide by 3 factorial, and that's because I have 3 5s. And then I still get 840. So it's very, very similar. It's really not that different of a method. Sometimes it just helps people to see it in this way, and it helps them to understand better. Okay, any questions so far? No, we're okay. Alrighty. Let's try another one. So we'll try a few. We'll kind of up the difficulty level as we continue on. So the next one here, we want to determine how many 7-digit numbers can be made from the digits 65435554. So we'll first start by using the formula. So n is my total number of elements, which in this case, 1, 2, 3, 4, 5, 6, 7. Then we have to figure out how many identical items there are. So first we'll look at the fives. So we have 1, 2, 3, 5s. So A will be our number of fives, and we have 3 of them. And then I look for any other identical elements, and we have our 4s. So that means B will be our number of 4s, and that will be equal to 2. So now, using the formula, n factorial all over a factorial b factorial, I will have 7 factorial all over 3 factorial for the 5s and 2 factorial for the 4s. So if I put all of that into my calculator, I get 420 different options. Now we'll also do this using the box technique just to give you a better idea. So we have 7 spots, 1, 2, 3, 4, 5, 6, 7. We first start by counting as if we don't have any identical elements. So 7 options for the first one, and 6, then 5, and 4, then 3, then 2, then 1. So we have 7 factorial, but we need to account for those identical elements. So we need to divide out the ways the 5s could all be switched around. So that's 3 factorial. That's because I have 3 5s. And then I need to divide by 2 factorial. And that's because I have 2 4s. So now I can just put that into my calculator, and it's the same thing as the other one. It's just one of these usually is easier for people to see. Okay, any questions so far? Same stuff as before, we just need to be mindful of those identical elements. Okay, so for 3, a wall design is to be made by lining up the following tiles. So we have 7 blue tiles, we have 4 green tiles, 6 red tiles, and 2 yellow tiles. If the order and distribution of the colors of the tiles is random, how many different designs can be made? So, depending on where the different colors are, it counts as a different design. This is how I know that order matters and this is a permutation. Now, if I just had one of the blue tiles first, if I swapped that out with a blue tile, it wouldn't change the order. It would be the same thing. So those are identical elements. So we will start by using our formula. So n is my total number of tiles. So I have 7 blue, plus 4 green, plus 6 red, plus 2 yellow. So 19 tiles in total. And now I need to account for my A, B, C's, and D's, or my identical elements. So A is my number of blues, so that will be 7. Then B will be my number of greens, which is 4. Then C is my number of red tiles, which is 6. And D is my number of yellow tiles, which is 2. So let's use the formula. So we have n factorial all over a factorial, b factorial, c factorial, d factorial. And that will be equal to 19 all over 7 factorial multiplied by 4 factorial multiplied by 6 factorial multiplied by 2 factorial. And if you put this whole thing into your calculator, and make sure you practice doing that so that you're confident with that, it's really, really big. We'll have 69 million, 698 million, 377,680 different ways. Now we can also use the box method for this, or the box technique, if you find that easier. I just want to show both for everybody. Now I don't have a lot of room to write out all the spaces, but we'll get the point. So we have 19 spots. I'm just going to quickly do it like this. Sorry for the bad form. I still have enough space. So we'll have 19, 18, 17. We basically just treat it as if it was normal. I just put the 3 dots because I don't have space to write out the middle bit. So that will equal 19 factorial different ways. And then I have to divide out the same numbers from over here. There we go. Divide out those. And I divide out the 7 because we have 7 blue tiles, and I need to account for all the arrangements of those mixing themselves up amongst one another. Same with the green. I divide by 4 factorial to account for the 4 greens being all swapped. We don't need to count that. Same with the reds. We don't need to account for the 6 reds getting all jumbled. And similarly for the yellows. So then we put that in our calculator and we get the same thing. 698,377,680. So the point is it's really, really similar to what we were doing yesterday. We're just accounting for those identical elements at the bottom. Okay, so last question, and this one is a little bit of a tricky one. So for 4, how many different 7-digit numbers can be made from the following digits? 853300, and all of the digits must be used, and the number cannot start with 0. It's very typical that we don't want the number to start with 0, because then it's not a 7-digit number anymore, right? If I had a 4-digit number like this, I could also write it like this, right? The 0 doesn't make it a 4-digit number, so we can't start with 0. So let's identify all of the different ways that we can arrange a 7-digit number. So I'm going to draw out all the spaces. I'm going to use the box technique for this one. So we have 1, 2, 3, 4, 5, 6, 7. Now we do have some restrictions here. The first one is that this first one can't be 0. And remember, it can't be 0 because we can't start it with 0 and still have it be a 7-digit number. So if I look at all of my different numbers, this one could be an 8, a 5, a 3, or a 3. So there's 5 options. When I'm putting together my options in the box technique, I don't worry about the identical elements, just count how many elements are there. So it can't be 0, so I eliminate the zeros, but there are still 5 other numbers. Even though 3 are 3s, we're not going to worry about that until the end. Then for my next spot, I have already used up one of the numbers. So I only have 6 numbers left, then 5, and 4, and 3, then 2, and then 1. And because I need a first number and a second number and a third and a fourth and a fifth and a sixth and a seventh, I'm going to multiply those. And then I need to multiply them and account for the identical elements. So I'll start by multiplying them. So I'll get 3,600. And now let's see if I have any identical elements. So I do have 2 zeros here. So we need to account for those 2 zeros being swapped. We're currently counting those as different arrangements, but they're not. So we need to divide out 2 factorials because we have 2 zeros. And then we also need to account for these 3 threes, right? So because in the current arrangement here that we've put together, the 3s are all individual, but we can move them around amongst each other as much as they want because they're identical. So we don't want to count those. So let's divide by that. So that's because we have 3 threes. And then you can put that into your calculator and we'll get 300. There we go. Just double checking that I did it all right. There we go. Okay, so we'll add in one more piece that makes it a little bit harder. So how many of these 7-digit numbers are even? So remember, we still can't have 0 at the beginning, but we need to figure out how many are even. So let's figure out how to know if a number is even. So for the number to be even, it must end in an 8 or a 0. Right? If you think of all of the even numbers, they all end in an even number. So we need to ensure that our 7-digit number is even, so it must have an even number on the end. Now take note of this word or here. Because I can have it ending in an 8 or a 0, I'm going to need to add those because that's my additive counting principle. So let's look at our 2 different cases. So the first case is when we end with 0, and then we'll do case 2 after, where we end with an 8. So let's figure out how many ways we can work with these 2 cases. So I'm just going to draw out my 7 spots. There we go. Now for this first one, the last one has to be a 0. So there's only one way that that can happen, right? So I'm just going to pick one of the zeros and put it there. I'm not going to worry about switching up which zeros which. I'm just going to put one of the zeros right there. Because remember, we treat this as if all of them are distinct, and then we'll deal with them after if we still have identical elements. So I'm going to put 1 0 there for sure. Then, if we recall from over here, we still can't start with 0. That's still happening. So that means we only have 5 options here because that one can only be 8, 5, 3, 3, or 3. Now for the other ones. Because we've already assigned 2 of the numbers, we have 5 choices here, 4 choices here, 3, 2, and 1. So within this part here, we have one of our zeros somewhere in there because it can't be at the beginning. And then we have our other zero on the end. So because one of our zeros has been actually placed and the first number can't be a zero, the only part that's kind of variable that could have other elements we're worried about is that middle bit. And in that middle bit, we only have one zero. So we don't need to worry about zero being a duplicate or an identical element anymore. So if I multiply all of that, I will get 600. And then I need to divide by 3 factorial because of the 3 threes. Now to reiterate, the reason why I'm not dividing for the 0 is because I assigned one of the zeros here and the other 0 is living in this middle part. So the part that's variable and can switch around, that only has 1 0 in it, so it's not a duplicated term anymore. So then this will be 100. So there's 100 ways for the number to end in a 0. So let's try case 2. So for case 2, we want to end in an 8. So 1, 2, 3, 4, 5, 6, 7. Now this last one has to be an 8. So there's only one way we can put in an 8 in that spot. And then over here, we still can't start with 0. So still for over here, we can start with 0, but now we think of how many we have. We can't start with 0, but 8 is already at the end. So we've already used 8, and we can't use 0. So all we have left is 5 and the 3 threes, so we only have 4 options here. Now for the ones in between, we'd have 5 left because we've already assigned 2 numbers, then 4, and 3, and 2, and 1. And then I'm going to multiply all that out, so 480. Now in this case, because of the variable stuff in the middle, the 2 zeros could be anywhere, and we're already accounting for them being separate. But we know they're not separate, they could swap. So in this case, we do have to account for the zeros because they're not in a set position, they're in the middle, being switched around, and we still need to account for the 3 threes, those haven't gone away. And that will be equal to 40. So now for our total, because we have either case 1 or case 2, I add them together and I get 140 different ways. So definitely a little bit more complex. I find the ones where it has to be even or something really, really challenging and super confusing. But that is it for our lesson.